Thanks everybody for joining this experiment channel. This time we will speak about cooling. We'll speak about heat transfer, and we will see in two presentations a different way of cooling using two different laws. The first is the Newton law and the second is the Fourier law. The Newton is the most simplified solution, most simplified description, and the Fourier is a little bit more complex, and we'll see in the next presentation. Okay, we'll see experiment of cooling first, then we get the physical law, and we compare the experiment we have done with a different example, with a different object, to check if the physical law is always the same. We need the material, we need two wooden cylinders, two wires, one pot with water, a thermocamera, the most important instrument, and the caliper. Then we prepare to fix the two cylinders by means of the wires. We heat the pot with the water and the cylinders in the microwave. We hang the cylinders by means of the wires, and we select the highest temperature spot option by the thermocamera. What we measure? We measure the temperature of the two cylinders at the corresponding time and the geometry of the cylinder and their weight. The mass of the cylinders are 20 grams equal, the diameter 20 millimeter and the length also 90 millimeter. They are equal. The starting temperature for the first cylinder is 80.5 centigrade and the final is almost 40. And the time during this cooling we measured is 780 seconds. For the second cylinder, the starting temperature is something lower, 68.5. The final temperature is 35.5 and the cooling time 660 seconds. On the right part of the sheet we see the two charts representing the point taken during the cooling of the two cylinders. Let's start some analytical development. We need to write an energy balance between the body and the ambient, which is a differential equation. At the first member we have the heat flow, so it's the derivative of the heat versus time, and which is equal to the mass of the body, the specific heat capacity, and the derivative of the temperature over the time. And at the second member we have the minus because the heat is released to the ambient. H, which is the heat transfer coefficient, a combination between convection and radiation. We will see afterwards how to calculate. The A is the surface of the body, and the differential temperature between the body and the ambient, T minus TA. This is a differential equation in the unknown function temperature of time and can be solved by a variable separation as displayed here. And the solution is given by integration of the respective members and gives the following function, which is a logarithmus of ratio between difference of temperature of the body, temperature of the ambient, and divided temperature of the body initial minus temperature of the ambient equals to a coefficient with minus made by these four variables times t. We can explain a different form eliminating by the logarithmus, and we can also take isolating the temperature. So we have an explicit function, temperature of time equals T0 minus TA times exponential function minus beta T plus TA. Beta is a constant, as told, is a ratio between the product HA and MC, and as the dimension of seconds to minus 1. If we apply the formula found to our experiment, we need to calculate the area of the wooden cylinder. Then we give the C, the constant of the heat specific constant by means of the literature. It's a cherry wood. And the H, this convection and radiation together, it's given by an empirical formula. The empirical formula is only valid for air and only for small bodies, and the temperature in the range of 100 degrees, 150. Otherwise, this is a more complex formula which involves a lot of parameters. The average temperature is the difference of the sum of the temperature of the body initial, the temperature of the ambient divided by 2, and in our case has two different values, 52.7 or 46.7 degrees. With the above, we can calculate the beta function for the first cylinder and for the second cylinder, and we can write the functions T1 for the first cylinder and T2 for the second cylinder's function of time. And here finally we have the chart of the found formulas, and we can compare the functions with the experimental values, and hopefully they are matching quite good in both cases. Now we want to challenge our formula and try with a different material. We are cooling now a potato, so we need 1 or 2 potatoes. We use 2 for statistical reason as before, and we need a pot with water, 1 bowl, thermocamera, caliper, and the preparation consists of cutting a potato into a sphere. This is important to have a simple geometry and to calculate the surface, to calculate all the parameters of the potato. Then we heat the potato in the microwave with water, of course, and we put the potato over an inverted bowl. This because it's very difficult to hang a potato. And then we switch the thermocamera to the highest temperature spot, and we measure the temperature of the potato at the corresponding times. And finally, we measure the geometry of the potato. In this case, it's only diameter, and we measure its weight. We evaluate. We get the experimental points displayed in this chart. The mass of the potato is 140 grams, diameter 60, and the ambient temperature is 25 degrees. The starting is 82.6 and the final is 33.7, and it takes 2,520 seconds, much longer than the wooden pieces, of course, because the potato has a different thermal property and also it's a higher weight. Now the big question, is the same equation valid also for the potato? We can calculate the formula because we have all the parameters. We get the area, we get the C from the literature, 3430 joule per kilogram per Kelvin. The H, the heat convection and radiation factor, we can calculate with the same formula, being the temperature average 53.8 degrees, and the beta is all therefore given, and with the beta is known the T function as written here below. If we compare the experimental data, which are the red spots, with the calculated formula, which is the orange line, we see that they are not matching. So the orange line is always laying above. It means the potato would have taken much more time to cool down. So it is not matching. Why is not matching? We'll see in the next presentation. So thanks for your attending, and thanks Newton for your strong contribution. We'll see